Cognitive neuroscience. So these notes will go roughly, kind of, sort of roughly with chapter 15 in your book, but we're just going to make them our own, okay? The real theme here, besides the label of cognitive neuroscience, is this right here, neural computing. You might hear a lot in cognitive psychology that the brain is a computer, right? And well, there is some potential validity to that. I'm going to fix my camera real quick. Sorry about that. There is some potential validity to the idea that we want to think of the brain as a computer. Certainly, there's plenty of debate in modern cognitive science about exactly that question. But certainly, it has a history in cognitive psychology, and this raises the question, of course, how can we um, how can we imagine something like the brain as actually functioning at all like a computer? We've just learned in the previous chapter about neurons and their role in learning and memory, and how we can maybe modify synapses to learn new things. Can we use that knowledge at all to inform our understanding of how the brain computes? We might want to start with, what do we mean by computation in the first place? There's a couple of definitions. Um, One, a formal definition of computation is called rule-based manipulation of symbols. We'll talk a little bit about that. Another way to think about computation or the brain as a computer is to talk about it in terms of information processing. And we can see how maybe some of the stuff we covered in the chapter on long-term potentiation might involve some sort of information processing, because the brain's ability to learn, to change as a function of repeated stimulation of the same synapses, is a way of storing information in the brain, right? If the brain is constantly changing as a result of experience, then we might describe the nature of those changes as a form of information being stored in the brain, right? So maybe that'll help us a little bit here. Now back to that question of or that other definition of computation as rule-based manipulation of symbols. That's going to be a little tricky, but let's give it a shot. We're going to start with what's called the neuron doctrine, right? And the idea of the neuron doctrine is that the neuron is the fundamental unit of the nervous system, and that things happen with neurons, or the connections between neurons, synapses, and so forth. So the origins of this in cognitive psychology is comes from McCulloch and Pitts. So way back in the early 40s, right? In the very earliest days of talking about information processing and digital computers. And it was proposed that we wanted to invent a machine that could possibly think and solve problems. This comes from the very earliest computers, guys like Alan Turing is noted here, the Turing machine. What's that? So Alan Turing, as part of his work, was working on designing a computer that could be a code breaker for the British during the war. And and so the idea is that that's a computational problem, because you're going to take symbols, you're going to take the encoded messages you get from the enemy, and you're going to try to manipulate those symbols in a way in which you try to find a pattern and decode that pattern. And that's a problem to be solved, of course, right? But it's a machine that can solve just that one very specific kind of problem. So we envision next, though, the possibility of being able to build a machine that can do more than solve just that problem. What about a machine that could solve many kinds of problems? And we might say that such a machine that could solve essentially any kind of problem it is presented with would be called a general problem solver. And that's what we kind of mean by an AI in many respects, right? Is a machine that could just take any information and solve any kind of problem. So Alan Turing envisions the idea of a machine that could solve problems and engage in this, again, so-called rule-based manipulation of symbols. And so he envisions the concept of a Turing machine to do this, right? A Turing machine is a machine that receives input in the form of various symbols, and then it manipulates that input by changing it in some way, and then it generates an output. And if it has the right input and enough ability to manipulate that information, it could generate output, and that output would be solving problems, right? The input would represent the problem to be solved, and the output would represent the solution to that. So next comes McCulloch and Pitts, and McCulloch and Pitts say, "Hey, that's kind of neat. Um, is it possible that if we're going to envision this kind of machine as a form of a general problem-solving artificial intelligence, does that mean that we can take that logic and take it back to the human brain and say that this is exactly what the brain is? The brain is something like a Turing machine. It receives input and it manipulates that input and generates output. And that's how humans solve problems. So, okay, that means brains are essentially big neural networks that are computers that solve problems. And now what we want to do is we want to go back to the idea of a computer and say, can I design a computer that works like a brain? So that way, if I can do this, if I can figure out a way to make a computer function more like a brain, then I've created something that we might call an artificial neural network, right? It imitates and simulates what brains do in terms of neural network processing of information. But obviously, it's not an actual real live biological living brain, right? It's a computer. So it's going to be something that works according to the same rules as a brain, as a neural network, but it's a computer, so it's artificial, right? So we're going to keep with the same thinking that we've had before about neurons having an activation thresholds, and they have synapses, presynaptic cells and postsynaptic cells. And so let's see what McCulloch and Pitts think about here. So again, we have these assumptions. We've got binary input, meaning you got a input coming from a presynaptic cell or you don't, right? You got a postsynaptic cell that has an activation threshold, so you have to hit that threshold for the postsynaptic cell to respond. And then if it does respond, you have an all or nothing response, right? Action potentials are binary in that regard, right? We also have, under our assumptions, weighted input. And we've talked about that before, right? We've talked about EPSPs, IPSPs, right? These graded potentials. You can have weak signals and strong signals coming in. And so a weak signal might not be enough to trigger the action potential. Stronger signal might, right? But we also have looked at long-term potentiation, long-term depression. So that means that these inputs can change their strength over time. So let's get what our starting point here. Imagine a neuron with an activation threshold of y, right? What is y? Well, it's a number to represent our action threshold, a variable to represent the activation threshold. We'll just call it y for now. And then we have two presynaptic neurons labeled x1 and x2. And maybe they have differing strengths in terms of the signals they send to our neuron y. What we're going to do now is we're going to build what we might label a wiring diagram, a circuit diagram. And we're going to design it in a way that this kind of circuit diagram can compute a decision, can make a decision. So what do we have here is we have two neurons called X1 and X2. They both synapse onto neuron Y, right? So Y is our postsynaptic neuron. As we're labeling here, Y has a threshold of 2. So that means that in order to fire its action potential, it has to get enough input that sums to 2, right? These numbers are just made up for our easy purposes here. But if we say that neuron X1 sends a signal of strength 1 to neuron Y, and neuron X2 also sends a signal of strength 1 to neuron Y, then individually, neither of those two neurons are going to be able to activate Y, right? Because it's just a signal of strength 1. But what if we combine them? So if both X1 and X2 are active at the same time, then they're going to converge. This is called spatial summation, going back to some of those notes on synapses we've covered before. So they can sum their inputs. And so now the 1 plus 1 equals 2. And so Y will respond to that. But importantly, Y will only respond if X1 is active and x2 is active, right? So that's why this is called an and function here, is that y's activity is dependent on the activity of x1 and x2. Now, in this kind of computing and decision rule language, we tend to use statements like true and false, right? So we're going to say that y is true. What does it mean to say y is true? Y is true if it's firing its action potential, if it's got a signal strong enough to cross its threshold and make it fire an action potential. So if y is active, we'll say that y is returning a value of true. If y is not active, it is sending a value of false, right? So is y true or is y false? Well, y is true if and only if x1 is true, because it's firing, and x2 is true, right? So let me say that again. Y is true if and only if x1 is true and x2 is true. And that's our and decision rule. If x1 and x2 are both true, then y is true, right? I got an example here in plain language, right? So let's say that I want to make a decision based on somebody offers me a job, and I want to say yes or true or accept to this job offer only if the salary is good and the location is good. So we can say that X1 represents the salary being above some threshold value, right? Some criterion. And X2 represents information about the location. And again, it's above some desirable criterion. So if both of those things are true, X1 is going to be active, right? Because the salary is good enough. X2 is going to be active because the location is good enough. And now they converge onto Y, and Y is true. And I say, yes, I take the job, right? So this is the kind of logic that we use to make decisions all the time. What the McCulloch and Pitts neuron shows here is that this kind of and function is a simple neural network that can execute such a decision. So this now takes us back to saying, is it this how we can imagine how the brain performs computations and decision making? Is that by combining these two inputs, I can determine whether some critical value has been met, and that allows me to say yes or no to this job offer, right? So that's neural computing, right? But that's just one function. That's an and function, right? One thing I want to say here, though, is that we want to use a couple other technical terms. Our X's, X1 and X2, this is called the input layer because this is the input into our neural network. And Y is the output layer. And it's the decision of Y, true or false, that determines the decision that we are making. It's a very simple neural network, right? It would just be 3 neurons potentially here. We can change this a little bit, though, because if we change the weights of X1 and X2, so this is our picture on the right, now the signal strength going from our X's to the Y is now 2. So this means that X1 all by itself is enough to activate Y. X2 all by itself is also enough to activate Y. So this is an OR function now because X1 could be enough or X2 could be enough to stimulate Y to fire its response, right? So if we changed our decision logic a little bit, someone offers me a job and I say, well, one of these things needs to be true. They either have to pay me a good salary or they need to offer for me to live in a good location. So if either one of these things is true, I'm going to say yes. So it could be a good salary but bad location. So X1 is true, but X2 is false, but I still get a signal. So how would that look, right? So X1 sends a signal of 2. X2 would send a signal of 0, right? If X2 is false because the location is bad, but I still have 2 plus 0 is 2, and that's enough to activate Y. Or it could be a bad salary but good location, so now X1 sends a signal of 0, but X2 sends a signal of 2, and now Y is active again. So we say yes to the job. But if neither is true, right? So it's bad salary and bad location, then I get zeros converging to Y. Y does not respond, so Y is false, and I say no to the job, right? So 2 very simple circuits, same general structure with 2 cells in the input layer, 1 cell in the output layer. All that we need to do is change the connection strength between the input layer and the output layer, and we can instantiate 2 different decision rules, right? An and decision rule and an or decision rule. What if we change it up a little bit again, right? So now all we're doing is we're just changing the connection strengths again. But now we've created a connection strength of a -1. So what in the world is -1 here? Well, we need to remember inhibition, right? So we talk a lot about synapses being excitatory, and I mentioned EPSPs, right? Those excitatory postsynaptic potentials, these graded potentials that depolarize a neuron and get it closer to its firing threshold. But an IPSP, an inhibitory postsynaptic potential, is one that hyperpolarizes the neuron and moves it away from its firing threshold. So in this case, we see that neuron X2, if it's true, that is, if there's something about X2 that is true, it's going to activate the signal from X2 to Y. It's going to inhibit Y. It's going to move it away from its decision rule or its threshold, right? So if X1 is true, so let's say this here. Let's say that salary is critical on our job offer. So I need X1 to be true, right? So if X1 is true, I hit my minimum salary. We're going to send a signal of strength 2 to neuron Y, and that could be enough for Y to respond with a true. But what is X2 measuring? So X2 is measuring a undesirable location decision here, right? So I'm going to say I don't particularly care about locations, but there might be a couple of places I definitely don't want to live. So if one of those cases is true, that they're offering me this job in some place I definitely don't want to go, then that turns out to be true, that I'm being sent to some bad place, right? So X2 is now true. And when we sum these inputs, 2 plus the -1 means 2 minus 1. It's 1, right? So that is not enough to activate Y, because even though X1 is stimulating Y and moving it towards its threshold, the simultaneous input from X2 moves it back down a little bit, right? Moves it down a notch. So Y would be false in this situation. So what we need is we need X1 to be true and we need X2 to be false, because if X2 is false, then it's sending a 0 to Y and the X1 signal will win out, right? This is called an and not function, because what we need is we need X1 to be true and we need X2 to be not true, right? So and not. X1 is true and X2 is not. Or X1 and not X2 is the simpler way to say it, right? X1 and not X2. Of course, you can flip it. So just to show the alternative way of framing it, we might suggest here that the salary isn't so important, but as long as it's above the cost of living of wherever it is you're going to send me. So X1 is true when the location is what I want, and X2 is true only when the salary is below the cutoff. And so we need an and not function here so that I can accept the job if they pay me enough to live wherever it is, right? So just flipping the decision, the actual specifics of the decision, but it's the same logic of the and not function here. Now what do we got? Okay, we've made it a little more complicated, but it's not super complicated maybe. So what we have now is called a hidden layer, because we still have our input layer X1 and X2, and we still have our output layer Y, but now we have a middle layer, and it's called a hidden layer. And so let's first look at that hidden layer, Z1 and Z2. And we look at what it's doing to Y. They both send a signal strength of 2 to Y, and we're going to still keep with this idea that Y's activation threshold is 2. So that is an OR rule, right? But what X1 and X2, what are they doing? Well, X1 is sending a 2 to Z1 and a -1 to Z2, and X2 is sending a 2 to Z2 and a -1 to Z1. So if we think about the effects here, Z1 is receiving an and not function where it wants X1 to be true and not X2. Z2 is also receiving an and not function, but it's the converse. It wants X2 to be true and not X1, right? So how does this work? This is called an XOR circuit or exclusive OR. And what this means with exclusive OR is that I'm going to do one thing or the other, but definitely not both, right? So an exclusive OR means I just want one thing to be true, and it doesn't matter which of those two things is true, but it's just one of those things and not both of those things. My example perhaps is a little bit weird, but imagine, for example, you go to a restaurant and they offer you dessert, and they say, you can have cake or you can have pie. Pick whichever one you want, and that's fine. So let's think about that. If X1 represents cake and X2 represents pie, you're offered cake. So you can say, okay, I'll have the cake. So cake is true, and you're not offered pie, so pie is false. So in this situation, X1 will send its positive 2 signal to Z1. X2 is false, so it does nothing on to Z1. Meanwhile, Z2 is false because it's not receiving any input from X2. It is being inhibited by X1 though, but that's okay. Z1 is still active and it's going to send a signal of strength 2 to Y, and you're going to say, I'll take the cake. You could be offered pie but not cake, in which case now X2 is active. So it activates Z2 and inhibits Z1. X1 is false, so it's basically doing nothing. So now Z2 sends a signal of strength 2 to Y, and you say, okay, I'll take the pie. But what if you go to a weird restaurant and you're told that in order to get dessert, you have to have both cake and pie. You must take cake and pie. So even though you are happy with cake or you're happy with pie, you don't want to be forced to take both. So how does this map out? Now X1 and X2 are both true. So now when X1 sends its excitation to Z1, X2 being also true is inhibiting Z1. And that means that Z1 is false because we have 2 plus minus 1, right? And then Z2 likewise is receiving excitation from X2, but it's also being inhibited by X1. So now Z2 is false because, again, it's receiving input of 2 minus 1. So now with Z1 and Z2 both being false, Y is false, and you end up saying no, right? So that's the way the logic of an XOR circuit works. If X1 is true or X2 is true, but not both of them, then I will say yes. But if both happen to be true, now I'm going to say no, right? So that's our XOR circuit. So by adding in a hidden layer with 2 more neurons, we can add a little more complexity to our decision-making rules. Now, this is as far as we're going to go when it comes to trying to build a artificial neural network, a circuit diagram like this that can execute a certain simple decision rule. But if you can follow along, that we can have these fairly simple diagrams that do and, or, and not, and XOR functions. Imagine what happens when we take a much bigger neural network that has maybe many input cells in its input layer and many cells in its output layer. There's a much greater complexity of decision-making rules that could be instantiated in such a network. And especially what happens if you start inserting even more hidden layers besides just the one hidden layer between the input and the output, then the complexity increases perhaps even exponentially. So when you think of an artificial neural network in 2026, when I'm making this video compared to the 1940s, when McCulloch and Pitts are imagining this, we're thinking of things that are far more complex with many more hidden layers that are doing more complex things. And so when you hear people talking about recursive neural networks or convolutional neural networks, that's referring to a lot of complex back and forth stuff that happens in these hidden layers that goes way beyond the simple details of the McCulloch and Pitts circuit diagrams, right? Now, there's one other thing we want to say about these, though. Let's not forget Hebb's law. We've been talking about it over and over and over again. So one of the things we might want to think about is that how do we go from an AND a circuit where you have input layers that have a signal strength of 1 to an OR circuit where they have a signal strength of 2. How do you get this kind of setup where you have signals coming in from different neurons that have different strengths? Well, that's what LTP is supposed to be about, right? Is that it can either increase or LTD might decrease the strength between two, the strength of a synapse between two neurons here, right? That's all Hebb's law. So, is it possible that we can then appeal to the idea that neural networks can change their activation strengths over time? Yes, and this is going to take us to another phase of neural network design here. This is called the perceptron, and this is called a perceptron because it was designed as a way to explain how a neural network might be able to recognize and therefore perceive something. So we have an input layer. The input layer is labeled here with the variable I. So we start with I sub 0. It's standard to start counting with 0 in computer science, all the way up to I of n minus 1. And all of these i's as part of the input layer will converge and sum their inputs, and that's where the summing function is here. So we have the sum of i's um, all converging to what's called an activation function. That's our y, that's our output, right? This activation function, if you notice, is a sigmoid graph, right? And the sigmoid makes a little S shape there, right? What that means is that if the sum is below the cutoff on the left-hand side, it returns a value of, say, -1, which is like a false. Otherwise, if it's on the right-hand side of that sigmoid where it's up above the x-axis, then it's a positive one. It's like a true, right? So this activation function, the sigmoid, is a binary decision rule that can essentially return a value of true or false. And that depends on whether the sum of all of these inputs, I through I sub 0, all the way up to however many i's we're counting here, hits a critical value. But notice there's another layer here labeled the weights, and those are the w's. So what this means is that the effect of I sub 0 on our sum function is going to depend on the strength of that signal. How important is the input I sub 0? How important is the input I sub 1? And so that's a different weight, W1, right? So we're going to have W0, W1, all the way up to however many i's there are, right? What in the world could this kind of thing do? What are we trying to do here? Well, let's imagine a situation, since I said this is meant to be a neural network that could recognize and perceive an object. Let's imagine what we want to do is we want to create essentially an artificial visual system that can recognize content in a digital photograph. So let's say that I want it to recognize a digital photograph of a duck. I'm choosing that because that's the example I've always used when I teach this course and the sensation and perception course. It comes from somewhere. I don't recall exactly where. So we're going to try to train this thing to recognize a picture of a duck. So I'm going to show it a photograph of a duck. And what represents the input layer? Well, what it's going to do is it's going to decode the information in this digital photograph. The information is the pixels in the photograph, right? So let's say we have a simple low resolution image that has maybe 256 pixels in it. Now we want to keep it simple here. We want to maybe treat this as a black and white photograph so we don't have to worry about color values. So I'm just going to encode information about the brightness level of each of these 256 pixels. And that's going to represent our input layer. So I'm going to have 256 i's in our input layer from I sub 0 all the way up to I of 255. That's our n minus 1, right? And that gives me 256 i's in our input layer. So my neural network is going to determine the brightness value of every pixel from I sub 0 to I sub 255. And then it's going to put a weight on each one of those, right? So what's the weight? How important is pixel 0 and how important is pixel 1? Well, at the beginning, we don't know, right? We simply just don't know. So it's maybe going to have a bunch of random weights. And it's going to sum all of this up and it's going to come up with a decision. And it might return a value of true, that's a duck. It might return a value of false, that's not a duck, right? And if it is correct, it's probably just going to be correct by chance, right? But I'm going to give it feedback. That's the critical part here, where I'm going to say, you got that right, right? So I've told it, you got it right. So there must be something about these weights that is working. But what if I give it a different photograph now of a duck, but it's still a duck, right? But it's a totally different photograph. So it's a lot of differences in the actual pixel values now. And it repeats the same process, but this time it says that's not a duck. It gets it wrong. And then I say, no, that's that's not correct. That is in fact a duck. And now I show it a third picture that's not a duck. And it's going to try to figure out, is this a duck or not? And maybe it gets it right. It says no, not a duck, so it returns a false. Come on. Or maybe it returns a value of true and says that is a duck. And I'm like, no, you're wrong, right? So what we're doing here is we are training the neural network, right? It is trying to figure out the appropriate weights to assign to these pixels. And by continuously giving it new images and letting it try to figure out, is this a duck or not? And then every time I give it feedback, I'm essentially telling it that you're performing well and the weight values that you have assigned to your input layer are working out just fine. But meanwhile, sometimes it's probably going to be wrong more often than it's right, especially early on in the training process, right? So every time I tell it that it is doing the wrong thing, it's making the wrong decision, what it has to do is it has to update those weights, and it starts changing those weights and going through various iterations to eventually settle in on a series of weight values that are making fewer mistakes instead of more mistakes. And this is what we mean by training a neural network at this point, right? And this could take thousands of images, right? We might have to put thousands and thousands of images through this thing before it finally finds the right set of weights to the input layer to make the correct decision. But once this is done, we would then say it's been trained, right? And we have then reset all of these weights, and therefore we're changing the values of those signal strengths, going from the neurons in the input layer to the decision rule. Does this look like anything we might see in actual vision? Right? This is the idea, is that we want to think about this as artificial neural networks, but ask the question of whether or not this behaves anything like um, a real neural network. And you might remember when we talked about visual processing that we have cells in the visual cortex that might work something like a simple artificial neural network, right? They return true and false values based on whether a set of statements is true or false. Like, is this line oriented in this particular direction? Yes or no, true or false, right? And so maybe that's how we can think about the activity of cells in the visual cortex. And then if I just jump ahead real quick and get to this next slide here, here is from a very recent paper from just a few years ago in which they took the findings of Hubel and Wiesel in the discovery of all of these simple cells and complex cells and so forth, and they constructed mathematically a neural network based on those physiological findings that is able to achieve the same degree of, of responding to visual stimuli. So here the argument is that they have created an artificial neural network that effectively captures the activity of simple cells and complex cells and could explain in computational terms exactly what's happening in the primary visual cortex here. Now, this doesn't necessarily solve the problem of visual object recognition, but it does show, again, that we can build an artificial neural network that sufficiently simulates phenomenon that we really have established with real visual processing. Whether this is in fact a correct theory of what the brain does is another question, but at least again we can build a neural network. And we're not going to get into all of the little details about exactly how this particular neural network works, but I just kind of want to point out that it's possible to build a neural network from these kinds of findings. All right. Next part of this content deals with social cognition and social neuroscience. And so I think we should probably stop the video here, and we will pick this up with one final video. Okay.